So in this video, we're going to close out Chapter 13 with Section 13.4, which is equilibrium calculations. And so looking through the learning outcomes and expectations, you guys feel free to pause here, read through those before we continue. All right, so 13.4, equilibrium calculations. And so we've done this discussion about this value of Q and K, right? We talked about Q being equal to K, the system is at equilibrium. Q is less than K, the reaction proceeds right. There's not enough reactants, there needs to be more products. Q is greater than K, it proceeds left. There's too much products, not enough reactants. We talked about Le Chatelier's principle and actually poking or perturbing this system to do what we want it to so it returns to that equilibrium constant. But we can go a step beyond that, not just knowing which way it's going to go, but we can also calculate the concentration when it reaches equilibrium again. We can say, okay, Q is not K, it's going to shift to reach equilibrium, but we can actually make a prediction based on the initial conditions what the final equilibrium concentration will be. And so the most common method to do this calculation is called a reaction table or an ice table / ice method. And it looks something like this. It basically has the reaction on the top. You have initial condition, the change that will occur, and then an equilibrium. And so you have an unknown X, and you solve for that unknown X. And so we'll just do a quick example of that. And so here's an example of a trans and cis-stilbene. So it's the same molecules. These are structural isomers. Turns out when you shine light on this, it does an isomerization. A similar mechanism exists in your eye, and that's how vision occurs. And so a really cool reaction, but a simple example where we have A on one side, B on the other side. And so let's say we know the equilibrium constant for this reaction is 24. Okay, that number already tells us something. It tells us it favors this like 24 more times than it does this one. It really wants products rather than reactants. Because K is greater than 1, it's at least a little bit greater than 1. But let's suppose we initially only start with cis-stilbene at a concentration of 0.85 moles per liter. And so we have a starting condition where we're starting with just this, and we know at equilibrium it'll favor this. And so how do we calculate this concentration at equilibrium? We know where we started, we got to figure out where we're going to go. And so the first thing you do is construct an ice table. Then you insert the known information into the ice table. Then you determine the change in X by essentially solving for X. And then you complete the table, and then you solve and calculate equilibrium concentrations. And so let's just walk through this journey with this particular problem. And so here's our ice table. Reactants over here, products over here. We have initial, change, equilibrium. That's where ice comes from. And so we need to fill in this table. And so what do we know from this particular problem here? Well, we know how much reactant we start with, and we know that we only have cis-stilbene, which means we have 0 of the trans-stilbene. And so cis-stilbene 0.85 moles, trans-stilbene 0. Okay, so now the question is, how will this change? All right, we know already that our equilibrium constant is 24. We can also calculate Q, which the trans is 0, the cis is 0.85, which means Q is 0. Q is less than K. And so intuitively, you should already know this number 24 favors products. There's 0 products. This has to shift to the right. There's no other way this reaction can go. And so that means this number has to decrease by some amount. And since there's a 1-to-1 ratio, this has to increase by some amount. And so effectively, you know what it's going to be when you reach equilibrium. It's this minus X, and then this plus X, or just X. And so that tells you the equilibrium condition. And so what this helps us do is we can solve for X as long as we know K, because we figured out the concentration at equilibrium. And so there's our equilibrium expression, products over reactions, products to stoichiometry over reactants to stoichiometry. The value of K is 24, and so we can plug in our unknown concentrations. And so it's X and 0.85X. And so after that, we can do algebra, and we can actually solve for this X. And so we know what the change is, 0.816. It says to get to equilibrium, it needs to decrease this by 0.816, increase this by 0.816. And so we plug 0.816 and we get our answer. And so this effectively tells us that the amount of trans-stilbene after it reaches equilibrium is 0.816, and this is 0.034. And so if you divide this by this, you get the number 24, which means it's at equilibrium condition. And so, yeah, really strong predictive capacity. But that was a relatively simple example where you had two species in a 1-to-1 ratio. Let's do a slightly more complex one where we have H2 plus I2 giving you 2HI. And so we can look at our equilibrium. It gives us an equilibrium constant in this particular calculation. The equilibrium constant K for the reaction is 54.3. Okay, so we know the number 54.3. That's where it wants to go. It wants to get to that equilibrium condition. And so the question is it at equilibrium? And so by doing this, we can calculate Q. We can essentially say, okay, how much HI do we start with? That's this number. How much of the H2 and the I, which is these numbers, you can plug them into the equilibrium equation. Well, in this case, it's reaction quotient equation, and you get a number of 19.5. And so that means Q is less than K. There's not enough product. There needs to be more product. This has to shift to the right to increase the amount of product. But we want to do our ICE table to figure out how much. And so we do the same thing. We have reactants here. We have products over here. Initial change equilibrium. In the problem, it gave us our starting point. But we also know it has to shift to the right. So what does that mean? This has to decrease by a certain amount. This has to decrease by a certain amount. And it turns out both of these have to decrease by the same amount. Why? Because every one of these has to react with one of these. This can't change differently than this. Both of these have to change the same. But this product has to increase by 2x. Why? Because for every one of these, you're generating two of these. And so this is why minus x, 2x is our change. And then we know at equilibrium we get this. And so we have our equilibrium equation. We know what our value is, 54.3. We can plug in these into that equation. We have one unknown. But all of a sudden, the algebra gets really, really messy, right? And so we can do our quadratic equation and get something like this, right? You can go through and cross-multiply and get all get it narrowed down to this right here. And then we can simplify it to this quadratic. And so when we have a quadratic, we can take that quadratic and plug it into the quadratic equation, right? X is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. We know what our a, b, and c values are. We can plug them into this equation, and we end up with two answers. The reason we have two answers is because you have to execute this twice. Once when you add, and once when you subtract this. And so by doing that problem twice, we get two different answers, 0.0114 and 0.00156. So you're like, okay, what is X actually? And it turns out there is only one physically realistic answer to this question. And so it really comes down to which one is actually conceptually viable? Which one can you actually plug in here and to get reasonable outcomes to them? And the answer is this number, 0.0156. And the reason we know that is if you plug this number in here, you get a negative concentration, which is physically impossible. And so anytime you do this quadratic to solve these problems, one of the two answers will be physically nonsensical. And so while you could plug X into this equation over here and it would give you a number, you can't plug it in here. You would get negative concentrations, which is not physically meaningful at all. And so the only possible answer is that one. And so, yeah, you have X, you can plug that in, you get your numbers for your equilibrium concentrations. And so you can see this math gets pretty complicated pretty quickly, especially if you have to do a quadratic equation. Thankfully, you can go to Wolfram Alpha and have those solve those math problems for you. But there's also an easier way. And it really comes down to this adage, sometimes close enough is good enough. And this is the art of engineering, right? Where you don't have to be exact, you just have to be good enough for what you're doing. And so sometimes we can simplify saying, you know, if K is small and the initial concentration of a species is relatively large, this X change might not matter that much. Basically, if it's not going to convert a lot to products, then maybe we can ignore X on some of this math. And so one of the threshold assumptions or a threshold value that people say is that if your initial concentration divided by K is greater than 400, then that X doesn't really change enough to really matter. And so getting rid of that X only introduces less than 5% error. And that's where this 400 number approximately comes from. But if that is less than 400, you can't get rid of X because X matters. And that would be a scenario where basically you're going to convert a lot of A into product. X is going to be a big number relative to A because K value is large. And so that's why you can't neglect X in certain circumstances. And so let's just go through one quick example of that. N2 plus O2 giving 2NO. We have a K of 1 times 10 to the minus 5, and we have a starting condition here. And so our starting condition, we've already learned something. We're starting with a bunch of this side of the equation and 0 of this side of the equation. The reaction can only go one way. And so you can actually calculate Q if you want. Because the product is 0, that's 0. It's automatically 0. In this case, Q is less than K. It has to shift right to generate more products. And so we can take our ice table. We know what our initial concentrations are from here, 0.8, 0.2, and 0. We know it's going to change. This will go down, this will go down, this will go up by 2x. And we know at equilibrium it'll look like this. And so we draw out our K equation, we plug in what we think it'll be at equilibrium, and then we're going to solve for X. And so we could do the quadratic formula for this, but we really have to ask yourselves, do I have to, right? Is X going to matter enough where I have to actually do that full math? And so if this concentration initial divided by K is greater than 400, we can neglect X. And so here's our initial concentration, 0.8. There's our equilibrium constant, 1 times 10 to the minus 5. 0.8 divided by 0.00001 is 80,000. 0.2 divided by the same is 20,000. And so both of these numbers are huge. It basically says our equilibrium constant is K is small. And so while we know it's going to shift to the right and generate more NO, this tells us it's not going to shift a whole lot. In fact, it's 10,000 times more favorable to be reactants than products for this equilibrium. And that's exactly what this math tells us. It basically says it will shift, but X is going to be negligibly small. And so what that lets us do is ignore this X. And so if we can do that, all of a sudden our equation simplifies a lot, right? No, we no longer have, cross multiplying and things like that. Instead, we've simplified the denominator to 0.8 times 0.2, and we can just solve for X. And so in this case, we're getting an approximate answer. Like we have clearly not done the exact calculation because X is not going to be 0. It is going to perturb this, but the question is how much. And so for X, we get 6.3 times 10 to the minus 4. We can look at this, plug in our X for these equations here. We basically say this is largely unchanged, this is largely unchanged, this one increases by a certain amount. And so doing this assumption, we have effectively created mass because these numbers have stayed the same and haven't decreased while they should when this increases. But the question is this good enough? And so we can plug these numbers into our equilibrium equation. We can say, okay, if these assumptions are okay, do we get approximately the right equilibrium constant? And the answer is yes. We get 1.05 times 10 to the minus 5 instead of 1.0 times 10 to the minus 5. And essentially, we have introduced effectively 5% error. And so we saved ourselves a lot of time and effort, but we got an answer that's good enough by assuming that X is negligible. And so again, is it good enough? In this case, yeah, it's within 5% error. That is acceptable for my estimations at least. So yeah, that's the ICE method. We're going to write a balanced equation. We have a reaction quotient. It tells us which way it's going to go. Typically, you're going to do these in molarity or atmospheres. We won't get into those details. You can compare Q with K and know which way the direction is going to go. You can construct your ICE table. You have reactants, you have products where you're starting. Your change is going to be minus X or plus X, depending on which way it shifts. And then you're going to have a product. And so after you have that ICE table filled out, you're going to essentially solve for X. And so you can substitute your values into the K equation and either solve for X directly, either simplified math or doing the quadratic equation, or you can simplify the math by saying X is negligible. If you have that, concentration of A over K is less than or greater than 400, then you can assume that X is negligible, and then you can solve for it that way. And you can recheck your math after that, and then you can find your equilibrium calculation quantities. And so once you have those equilibrium values, you can plug them back in the equation and see how close you are to the true value of K, and that tells you if you found that equilibrium condition. So yeah, that's equilibrium calculations. We're not a math-intensive class, but it is worthwhile to think about, not just in this problem solving, but just in general, that you know where you are, you know where you want to go, what change has to happen in between. That's kind of what the ICE table does in a formalized nomenclature way, and it'll help you out in lab if you can do that math. So yeah, that closes out chapter 13. Next, we'll dive into chapter 14, where we'll start talking about acid-base chemistry.